I'm going to talk about one particular impact crater on the moon for my talk, and that's Giordano Bruno, which is a 22-kilometer diameter impact crater on the limb just on the far side, and it's a very fresh, fairly youthful crater. And what we're doing is looking at the craters that have accumulated on its impact ejecta and comparing that with the thermophysical properties that we observe using the Diviner instrument on the Lunar Reconnaissance Orbiter. And what I'm showing here is an oblique LROC image of Giordano Bruno looking west. And the image on the right is a mosaic of LROC NAC images draped over topography and shaded with rock abundance that's been derived by the Diviner instrument. And what you see is that the interior and the ejecta of Giordano Bruno are very rocky. It's actually one of the rockiest locations we observe with Diviner on the moon, and that's due to the fact that this is such a young impact. And we have a similar data set that shows the nighttime temperatures. And again, we can see that this is a very warm feature at night. It takes a long time to cool off, so the material has a higher thermal inertia than what is typical for lunar regolith. So Giordano Bruno is probably no more than a few million years, and since it's undergone such minimal disruption from its initial conditions, this really provides a nice study area to look at the early stages of regolith development and overturn by impacts. It's got a very heterogeneous signature thermally, and it's also been noted that the craters on the ejecta, the size frequency distribution varies quite a bit depending on where you look on the ejecta. And there was a recent paper by Pleisch and Robinson, and they attributed a lot of this to the fact that most of these craters are probably or very likely to be self-secondary craters. So these are craters formed by fragments ejected at high angles that then fall back onto the ejecta after it's in place and populate the ejecta sort of near instantaneously with impact craters. But we also find that a lot of the variation we're seeing in the crater population correlates with the thermophysical properties. So we're suggesting that there's also, that the terrain is influencing the size frequency distribution as well. And a lot of this is probably due to the presence of large blocks and impact melt. And in fact, the blocky areas were excluded in the survey by Pleisch and Robinson for this reason. So why do we care about this? Well, part of the reason is that the chronology models rely on correlating cosmic ray exposure ages of Copernican craters to the crater counts on the ejecta of those craters. So I'm showing the Neuk et al. Chronology model here, and all the data points in the Copernican that anchor this chronology are related to crater counts conducted on ejecta. And so the assumption is that the ejecta blankets create an annulus around the crater that has reset the craters, erased the craters, and then the subsequent accumulation of craters provides chronometric information. And so if there are self-secondaries or if the terrain is influencing the distribution of craters, that would be a source of error in these models. So it'd be good to try to understand how these are influencing model ages. Especially when we look at, say, like Cone Crater and North Ray, where these are fairly small craters. You only have pretty small craters to use, and they're also fairly young craters themselves. And some previous work has shown that there are discrepancies in the crater counts around these craters as well. So a brief overview of Diviner. Diviner is a radiometer. It's one of 7 instruments on LRO, and we have 9 spectral channels that include visible out to IR. We nominally just operate in a nadir pointing, a push broom configuration, and we just ride along with the spacecraft looking down. And this is sort of shown pictorially here, where we did this is one orbit track across Giordano Bruno in the nighttime, and we look at the emitted radiance and convert that to brightness temperatures, and then we can use the 7 IR channels to back out the bolometric temperatures. And we get an observation roughly about every 1/10 of a second from 21 channels for each detector. So we have a pretty big data set now because we've been operating actually over 11 years now. So some early work we did, we looked at a single orbit that crossed the eastern side of the ejecta on Giordano Bruno. And I'm showing here a single orbit track for channel 4 and our channel 7. So channel 4 is shorter wavelength than channel 7. And one thing to note is that the temperatures vary quite a bit across the ejecta, implying that there is definitely a heterogeneity in the thermophysical properties of the ejecta. And that the fact that the two channels have noticeably different temperatures also implies that there's a lot of mixtures of different temperatures within the field of view. So just due to the nonlinearity of the Planck function, when you have a mixture of temperatures, the shorter wavelengths tend to be more sensitive to the warmer temperatures in the scene. And so what I've done here is difference the two channels to highlight areas that have greater amounts of what we call anisothermality, or difference in the different channels. And so the areas that show up with sort of the red and yellow in this plot are characteristically have a lot of blocks that are visible in LROC-NAC images. And then areas that have lower anisothermality typically just have a more uniform granular texture at the LROC resolution. And what we noted was that the density of craters decreased in areas where the anisothermality increased. So areas that were blockier had fewer craters. And so we've gone ahead and expanded on this work, and we've now built out a survey that includes most of the ejecta at this point. I've been doing counts along the east side, and my collaborator Azmi Patari has been working on the west. And you should note that he's had a much harder time than I have, so he hasn't covered as much area, but we noticed right away that there's a very distinct asymmetry in the density of craters, and there are far more craters on the west side than the east. So we're having, it's a little bit slower going to fill in the west, but this is our progress so far. And comparing the density of craters with rock abundance and nighttime regolith temperatures, we do see a correlation between these data sets. And so again, we confirm that in fact, as rock abundances increase, or as nighttime regolith temperatures get warmer, we see a systematic decrease in the number of craters that are observed. So what does this mean for model ages if we're trying to use crater counts to date the surface of the ejecta? Well, here I've split the rock abundance into areas of high versus low rock abundance, where high is rock abundance is above 10%, and low areas that are below 5%, and shown by the contours here. And you get a spread in ages of something like 3 million years to about 11 million years. So this sort of gives an idea of the sort of errors you get depending on where you're counting. And similarly, we can split up the regolith temperatures into warmer versus cooler. And you see a similar discrepancy in the model ages, depending on where you conduct your counts. And so Azmin did his counts in incrementally in these little boxes here. And so we just took these boxes and plotted the counts in each one of these and derived model ages. And again, this gives another idea of how the model ages vary across the ejecta depending on where you do your counts. And again, we see a pretty large discrepancy, something younger than 3 million years to up to 16 million years, depending on where you do your counts. So, what's going on here? We definitely see that the crater population on the ejecta varies with the thermophysical properties observed by Diviner. And so this does suggest that the crater formation is being influenced by the terrain characteristics. Rocky areas systematically yield younger absolute model ages. And so these areas typically are characterized by large blocks. So one suggestion is that the boulders are inhibiting the formation of craters. So we're looking at fairly small craters on the surface here. The impactors are probably comparable in size to the boulders themselves that they're hitting. And so typical crater scaling relationships are probably out the window. And if a lot of these craters are self-secondaries, these are lower energy impacts, so that might even be more important in this case. So there's a recent study by Rush et al. That supports this idea. They surveyed fragmented blocks on different Copernican age craters, and they found plenty of fragmented blocks, but they found that the fraction of fragmented blocks systematically increased with the age of the crater they were looking at, and that estimates of the energy frequency distribution of the projectiles that were required to disrupt the blocks were pretty consistent with the impact flux. And there's plenty of examples on Giordano Bruno. I've shown one here of a fragmented block. So that's part of the story, or at least we think is part of the story. But the other part of the story is that there's a lot of impact melts on part of the ejecta as well that might be influencing the size distribution of craters. So here I've taken a sample area. We have a really nice example of a flow where impact melt was in place by flowing down slope. And if you compare the size frequency distribution of craters on impact melt and compare it with the craters on the clastic ejecta right next to it, you get a very different distribution of craters. And so what I've done here is compared a couple different models. So the figure on the left here, I'm showing some model isochrons derived from taking the observed bolide flux from the Brown et al. 2002, actually that Sergey just showed in his talk, and scaled those to equivalent craters on the moon, but then assumed different target properties in scaling the craters. So here I'm showing dry sand, lunar regolith, and then a hard rock target material. And so the nominal lunar regolith, this is using the Holsapple values from his work. And so his nominal lunar regolith yields actually a pretty good match to the Neukom et al. Production function shown here. And if we just assume nominal regolith, we actually get a pretty large discrepancy in model ages. So, you know, for the melt, you get something that's less than 1 million years in age. And for the clastic ejecta, you get something around 8 million years. Now, if we then assume that the impact melt is hard rock and apply that model, that discrepancy is diminished quite a bit. So, you know, there could be target property issues here at play as well that are affecting how the craters scale. So I took some diviner data from a couple of spots on the ejecta. So here we're looking at the south part of the ejecta. So a lot of melt is here on the south rim. That flow I just showed you is right here. This is and here's the rim and part of the NAC frame. Here I've colorized it with our rock abundance data set and outline that flow here as well. And, you know, interestingly, the melt doesn't show up as pure rock and the rock abundance. And these really high rocky areas are areas where there are a lot of boulders right on the surface. So these show up as the rockiest areas. But the nighttime cooling of these areas all show that the properties of this material is not like normal regolith. So nominal regolith cools much more rapidly in the nighttime and cools to much lower temperatures. So the typical temperatures at this latitude are shown in the black here, and all these materials are much warmer in the evening. So the nighttime temperatures are really sensitive to the thermophysical properties of the near surface, basically the material within the thermal skin depth. And so as the sun sets and the sensible heat stored in the subsurface during the day starts to radiate back out to space, heat from lower and lower layers in the regolith start to make their way to the surface and are radiated, and we see that in our instrument. And so this gives us, by observing the nighttime temperatures, this tells us something about the vertical profile of the thermophysical properties. And so typical regolith has a very low density, fluffy upper layer that transitions pretty quickly to a higher density layer at depth. And it's pretty well characterized by an exponential curve with this E-folding depth, or H, sort of H parameter, typically between 5 and 10 centimeters. Now we can compare this with some of these areas that we've pulled data from on Giordano Bruno. And interestingly, the impact melt and clastic ejecta actually cool differently. And the fact that the cooling curves cross each other implies they have a different vertical scaling. And so fitting these cooling curves with models, we can infer that in fact the thermal inertia of the material has to be much higher than typical lunar regolith. And in fact, the classic ejecta is much better fit with a uniform distribution of material. And then the impact melt, because it cools quickly early in the evening, requires some low thermal inertia material at the surface, but then at depth has a much higher thermal inertia. And when I use thermal inertia here, I'm assuming a constant temperature because conductivity and other thermophysical properties are temperature dependent. But this at least gives you an idea of how this differs from typical regolith. So the point being, this material is different and it varies quite a bit. It's very heterogeneous. And so how this might be affecting or influencing the size frequency distributions is something we want to look a little more closely at. And then of course the other part of the equation here is the evidence for self-secondaries. And there's a lot of evidence that there in fact was a population of craters that formed on the ejecta because we see impact melt that has flowed in partially filled circular depression. So those had to have been in place before the melt was in place. Okay, so in conclusion, we see the distribution of craters on the ejecta is very heterogeneous, and the density of craters seems to vary with the thermophysical properties that are observed by diviners. So rocky, warm areas have fewer craters, and they give you younger absolute model ages. And so because a lot of these rocky areas have few craters, that may suggest boulders are inhibiting crater formation. And there's also a hint that maybe target strength is influencing the crater scaling in different ways across the ejecta. And certainly there's evidence for self-secondaries as well. So that's part of the story. The classic ejecta has probably a population of self-secondaries that are absent on the melts. So anyways, this is potentially a source of error when we're trying to match up cosmic ray exposure ages to craters. Something we need to consider, especially if we get new samples and do new sample returns and we try to age date crater formation. And with that, I'll hand it back to you, Michelle. Thank you.
Thanks, Jean-Pierre. Very interesting talk. So it does look like we have some questions in the chat, if Stuart wants to take that over.
Yeah, sure. So first up was Paul Wren. The question was, are you planning to look at methods to distinguish secondaries from primary impacts?
Not necessarily. If you look at the craters, they certainly, I've had conversations with both Pleicher and Robinson about, their work, and they'll argue that almost all the craters are self-secondaries. And at first I was pretty skeptical of that, but, doing the survey just sort of by eye and looking at the morphology of craters, that yeah, they might be right. Most of these craters may be self-secondaries, which is kind of alarming. Whether we can systematically distinguish them or not, I'm not sure. I mean, it's pretty clear where there's impact melt and there's impact melt in the crater. It's pretty obvious it's a self-secondary. But yeah, it's kind of trying to separate which ones are primary and which ones are secondary. It's kind of a daunting task. So I don't think we'll go that far.
Okay, the next question is from Clark Chapman. Are you sure the east-west crater density difference isn't partially due to personal equations? That is, have the two of you switched sides and counted small areas to compare if you get the same densities of craters in the same region? Also, is the spatial density of blocks great enough to stop formation of a large fraction of would-be craters?
Yeah, that's a really good question. I have done some counts on the west side myself, and from what I can tell, our counts are consistent, but it is a good point that we should sort of calibrate our counts just to make sure there isn't personal bias. So that is a good point. As far as the density of blocks and whether they could explain the discrepancy, that's something we actually would like to model. And then Emily Costello has a impact regolith overturn model that we're hoping to actually use in future work.
Okay, the next question, I apologize if I mispronounce your name, is from Nadav Nahaman. The question is, does this work change any absolute model ages of areas of older ages, although the rock abundance is obviously much smaller?
Yeah, I mean, that's a great question. So I think the question here is, how long does it take for this kind of heterogeneity to get homogenized by small impacts and kind of reworked into what we would consider nominal regolith? And again, that's where we want to do some more of the impact regolith overturn modeling to maybe get at that question. Like how non-uniform was Cone Crater when it initially started, and then how is it compared to now? I mean, I don't really know the answer offhand, but it's something we kind of want to get a better handle on. It's one of the reasons why we're starting to do this work. So good question, yeah.
All right, the next question is from Paul Schenk. In the conclusion slide, the 3 examples of units all have quote unquote fewer craters. Which has more?
Is this talking about bouldery areas versus impact melts? I think maybe that's.
I'm not entirely sure. You do have the bullet point that says impact melts have fewer craters. Target strength. I'm not entirely sure. He says yes. Paul says yes.
Yeah, I haven't really directly compared yet the rockiest blocky areas versus the impact melt. That's actually a really good question. That's, obviously this is ongoing work. We're still finishing out our survey of craters, but that's exactly the kind of thing we want to start mapping out once we get this done. So I don't have an answer yet, but that will hopefully be answered soon.
All right, next is Megan Hoffman. Question, is there a way to account for the terrain effects other than excluding areas of higher rock abundance?
Other ways of excluding area. I mean, I suppose you can come up with other ways of slicing and dicing the craters. We just chose rock abundance and the temperatures, which, I mean, in this case, the rock abundance and the temperatures are pretty well correlated. And that's telling us something about, I mean, the temperatures really tell us something about variations in the thermophysical properties, which we can model, which is why I kind of threw in the slide at the end showing some modeling results that might give us a handle on how the properties of the ejecta may vary laterally. So again, that's something we want to look more closely at and maybe come up with other ways of parsing the ejecta and see how it, the magnitude of all these variations on the crater size frequency distributions, we're still trying to work that out. So this work's still kind of in its early stages.
The next question is from Mike Zanetti, and this will be the next to last one. Anything else will go into the discussion. So Mike Zanetti asks, what do you think we as a community have to do to better understand self-secondary cratering? Lots more counts?
Yeah, that's a good question.
And this one might actually be better to just hold off for the discussion section if you want.
Okay, I mean, either way, I'm not sure what observations or crater counts we can do other than maybe try to compare counts on Copernican craters that are maybe a little bit older, and just to see how the ratio of, maybe get a handle on the ratio of primaries to self-secondaries over time. I don't really have a good answer for how the self-secondaries maybe pollute our crater counts in other craters, and that's something I think we need to understand better. And maybe some modeling. I'm not a modeler for the dynamics of the impacts and how they create these fragments, but maybe that's the direction to look at too.